Okay, so today's topic is the screen visible to you? Anyone? Yes, screen is visible. Please help me.
Yes, it's visible.
Okay. Okay, so let's assume we want to perform some computation. We want to perform some computation. We want to compute k, which is actually 7a plus 5c. Okay, and let's assume. So we say that what are our assumptions? So now, what is my assumption now? So my assumption is my assumption. What is assumption? So my assumption is that A and C are 4-bit data. Any question? So A and C are 4-bit data. So A is 4-bit and C is 4-bit. So since C is 4 bits, so then this is actually C3, C2, C1, and C0. Okay. So now the question number one for all of you. Question number one. So how many bits? So how many bits will be required for k to avoid loss of data? And what is our second assumption? So my second assumption is that, so now this is my second assumption. Assumption is that A and C are unsigned numbers. Can you now tell me now how many bits will be required for k to avoid loss of data? Can you now tell me? Yes. If anyone will answer this question, will get one bonus mark. Yes. Anyone who will answer this question will get one bonus mark. Yes. Yes.
It'd be
No
8
answer.
bits
Why 8 bits? Can you give me the logical argument for 8 bits? Why 8 bits? So now your answer is why 8 bits?
because if we assume the largest value for A and C, which would be 15, uh,
Mm-hmm.
the maximum value K could take is 180. So we'd need the range from 0 to 2 to the power of 8, which is 8 bits.
So who is answering me this? Who is answering me this? What's your good name?
It's moving. That's me.
Okay, okay. Now let's see. Whatever you have said, then I will do it. Okay. Now can you see here? So how many bits will be required for k to avoid loss of data? So now can you see here? So now please record here. So what is the maximum value of a? So that is the maximum value of a. So first we need to do what's the maximum of a. The question is, what's the maximum value? Since A is 4-bit, because please look at the assumption here. So A is N and C are 4-bit data. So A is 4-bit. So now A is 4-bit. So our assumption is this 8 is 4-bit. So what is the maximum value of A? It's a 4-bit value, so it will range from 0 to 15. So the maximum value of A is now 15. What will be the maximum value of C? The maximum value of C. C is also a 15 bits. So C is also a 4-bit data. So the maximum value of C will also be 15. Why it is 15? Because the A is 4 bits. So the maximum value is actually true for n minus 1. And what is n here? So this is actually true for 4 minus 1, which is actually 15. So the maximum value of A is 15. And similarly, since C is also a 4-bit data, C is also 4-bit, so is also 4-bit. So the maximum value of C is also 15. Any question? Okay, now the question arises, what is the maximum value of K? So the question arises, what is the maximum value of K? So the maximum value of K, we need to compute it. So how can we compute? So say is equal to 7, and then we multiply 7 with 15 plus and 5, and we multiply 15 with thing. So now what you can see, 15 sevens are 105, and plus 15 multiplied 5 is 75. This is actually equal to 180. So this is now 180. So k is now 180. So how many bits will be used to represent 180? How many bits will be used? So how many bits are required for 80 to 180? So basically the number of bits that you required for 80 is actually, okay, what is 2 power 7? 2 power 7 is actually what, 128, and 2 power 8 is 256. So can we see here? So now we can say that now this 180 lies within 128 and 256. So the number of bits that is required for k will be 8 bits. Any question? Any question? Should we proceed? If there is any question, please let me know. It's clear? At least say something. There are 17 participants now. Yes, Sidra. Is it clear, Sidra? Please speak in mic. Ghala, Fiza.
Yes,
Abdullah?
Professor, it's clear.
Okay, that's good. So now this is clear. So now what we can do. So now this is how it's worked. Okay, now we are going to do this. So now basically we need to compute. So this is now we need to compute what? We need to compute k is equal to 7a plus 5. So we need to compute k is equal to. So now what I'm doing, I'm using now different color. So this is actually 7a, and then plus, and I'm using the green color plus 5c. So now if you look at the block diagram of this, so the block diagram will look like this. So now we have the first input, which is a. So a, the first input is a. So this is a, this is 4 bits. So this is a3, a2, a1, and a0. The second input is c. So this is actually c3, c2, c1, and c0. And now my output is k, and we know that for k we need how many bits? 8 bits. We determined it. So we have K7, K6, K5, K4, K3, K2, K1, and K0. So this for K we need 8 bits, and we derived it using the next slide, the previous slide. And now we have A, which is actually 4 bits, and now we have C, which is also how many bits? 4 bits. Any question? And we derived this is in the previous. And what was our assumption? So the assumption was this was our assumption, that a and c are unsigned number, and a and c are 4-bit data. If we change the assumption, definitely the range will be different. Any question? Should we proceed? Now the question arises that how can we design this system using full adder? So the question arises. Now there is a question arises. So now the question arises. So there is a question. Now there is a question. So if we want, how can we design this operation using full adders and half adders if necessary? We need to use, okay, so the so this we need to so need to use we need to use minimum number of resources. Any question? Any question? So what I'm going to do now in the next slide, what I'm going to do, so now we have this thingy, which is actually 7a plus 5c. Control C, and then what I'm going to do, I'm pasting it here as an image. This is my image. We need to compute this 7 k is equal to 7a plus 5c, and now we also need to do this thing. So now this is the block diagram of the system. So this is the block diagram of the system. Control C, and then what I'm going to do it here, I'm pasting it here. You got it or not got it? Any question? If there is any question, please let me know. So now can we see here? Okay. Now the problem is that. So how can we design this system using the shift operation? Okay. Now if you look at here, now how can we compute 7a? So now there are things, two ways to compute 7a. So now what I'm going to do, so now we can compute 7a using, you can 7a can be computed as 4a plus 2a plus a. Okay, this is method number one. Because what we do, we want to compute this operation as the order of 2. Okay, is there method number one? What's the best method to compute 7a? Can you tell me of the order of 2? How can we compute? This is method number one. Okay, how many adders do we require? So we require one adder and one adder. So we require 2 adders. How can we do it efficiently? Can anyone tell me? Yes. Anyone may tell. Anyone may tell. Yes. Mubin. Yes.
Yes, Professor, I'm thinking.
Okay. Yes. Anyone may help. Anyone may help. Please, anyone may help. It's just like, oh. So we can compute it efficiently. Can we do it? So this is okay. Now the method number two. So now what I'm method number two. So 7a can also be computed at 8a minus a, which is method number two. Which method is better? Method one or method two? Yes, because this is also order of two. This is also order of two. All these numbers are order of two. This is order of two. This is also order of two. Any question? So method one is better or method two is better? Yes. Can you tell me? Yes. Method 2 is better. Why it's better? Why?
Is it because you only need one adder?
Yes, it requires only one adder. It requires only one adder. And then I will also explain this with another example. So let's assume now let's assume if we say, okay, now can you see here, now let's assume if we want to compute, so what I'm going to do, so I'm pasting, and let's assume we want to compute, let's assume 31a. Okay, we want to compute 31a. Method number one, which is an inefficient method, 31 way, we want to do it in a multiple of 2. So we can do it like this: 16a plus 8a. 16 plus 8 is 24, plus 4a, which is 28, plus 2a plus a. This is method one. And then 31a can also be used using the second method, 31a. How can we compute 31a? Yes, 32a minus a. Method 2. Which method is better? Can anyone tell me? So the question arises, which method is better? Anyone? Yes. One or two? Please help me.
Method 2.
Method 2 is better. Why method 2 is better? Why? Why?
It uses less operations.
Yes, method 2, very good. Thank you. Very good. It's a very good term. It uses less operation. Following the same thing, let's assume, I'm giving you another example. Let's assume we want to compute, let's assume we want to compute 60a. Okay, the first inefficient method can be used. How can we use 60a? So 16a can be used as 32a plus 16a, which is actually 48a, plus 8a, and 48 plus 8 is 56, plus 4a. Okay, this is method 1. How can we compute 60a efficiently? Can anyone tell me? Yes. How can we do it efficiently? Yes. Just digital logic, digital system design, number system. Anyone may help.
64a minus 4a.
64a minus 4a. So this is method 2. So it means that now method 2. Am I recording this lecture? Yes. Yeah. Yeah, it's being recorded, so it's not a problem. Sorry, I just okay. So now why method 2 is better? Why? Because method 2 uses what? Again, less operation. Okay. Now having said that, now this is like how some the other thing. So now what we note, one now in this point of time, we need to compute k, which is equal to 7a plus 5c. Okay, how can we rewrite this expression? So how can we rewrite this expression? So this expression can be rewrite is actually k is equal to, now how can we, so it is actually 8a minus a, okay, and then plus 5c. What can I write? So we can see 4c plus c. Am I right or not? Can I write this expression? Anyone? Yes or no?
Yes, Lucas.
Yes. Okay. Now we go further. So now when we go further, so can we write something like this? So k is now equal to. So now what I can say? So we can say, can I write 8a, which is actually the binary, because, and then one we can see when you can say a 2's complement. Why? Because minus a is equal to the 2's complement of a. Any question? And then what I can write, so that you can see, now we can see 4c, which is the binary of c, plus c, which is the binary of c. Any question? Any question? Should we proceed?
Yes, Professor.
Okay, now if we proceed further, so now please look at here. Now if we proceed further, so now what I'm going to do, so can we see, this is, can I write something like this? So can I write further, so I can further write it something like this. So now I can say this is now 8a of 2's complement plus a 1's complement plus 1. Why? What is now the 2's complement? So the 2's complement of a is now equal to a 1's complement plus 1. Any question? And then what can I write here? So now what I can write here, it is actually 4c of 2 plus c of 2. Any question? Any question? Clear? So now can you see here now what I'm going to do? So now I'm going to do, so this is actually now the 2's complement of A, and this 2's complement of A is equal to 1's complement of A plus 1. And we already did it before. So this is not going to do that. Any question? Should we proceed or no? If this is clear or not? If this is not clear or not, proceed. Yes, please go ahead. Anyone?
It's clear, Professor.
That's good. That's good. At least answer me, please. Please answer me quickly so that I'm. Otherwise, it will make me sad. Okay. So what we are going to do now? So what I'm going to do? So now what I'm going to do? So I'm going to copy this. So basically, I'm going to copy this thingy. Okay. Control C, and I'm going to the next slide. And then I'm pasting it here. Control C. So I'm pasting it as an image. So this is now we want to do this. Sorry, this is there. So this is actually this is now here. Now we want to do that, and now this is my figure that I control is to control C here, and then I'm pasting it here. Any question? Clear? This is clear or not? Yes, students.
Yes, Professor.
Okay, so what I'm going to do now, what I'm going to do, copy, and then I'm pasting it here. Any question? So what I'm going to do now, so now can we see here? Okay, now we want to compute this expression k. Okay, for that k, we need a binary of a. Please remember now 8a. How can we now compute 8a? So now what we are going to do is I'm using different colors. Okay, so the first color that I'm using is now the red color. So we want to compute 8a in binary. How many zeros we need to insert? Can you tell me? How many zero for 8a?
Three.
Anyone may answer.
Three.
Hmm?
Three.
Very good. So we need to insert three zeros. So now we need to insert three. So 0, 0, 0, and then we have A0, A1, A2, and A3. Any question? Any question? Okay. So what I'm going to do? So now why I'm not doing it like here? So now what I'm going to do? So okay, just I want to make this a little bit here. So this is actually, so we have a big, can you see here? So now we have a3, then a2. One minute. Why I'm doing this? Because it's, we need a3, we need a2, then we need a1, then we need a0, and then we need three zeros here. Any question? Okay. Now the second thing. Now second thing is, now we want to compute a ones complement of a. So now we have the ones complement of a. This is now tricky. Please remember, this is now tricky. Okay. Now, please remember, if we say, now this is my binary of A. So what is my binary of A? So my binary of A is now, actually, it is actually A0, A1, A2, and A3. But now we want to compute the ones complement of A. Okay, and then if you look at, if we expand this thing to extend it, so it is actually 0, then 0, and 0. So this now is a is now in uh, 7 bits, because 1 2 3 4 5 6 7. So this 8a2 is now 7 bits. Since this 8a2 is now 7 bits, so we also want to compute a2 as a 7 bits. So now I want to compute the ones complement of a. If I want to compute the ones complement of a, what should I write? Can anyone help me? What should I write here?
A bar.
The least significant. A0 bar. Then help me.
A1 bar, A2 bar, A3 bar.
A2 bar, and then A3 bar. Any question? Okay, now we have three zeros, because we also want to add it with this. Since we have these three, so we also invert these zeros, because these are unsigned numbers. So these are some unsigned numbers. So then we have some zeros. So then we have one here and one here and one here. Any question? Any question? Should we proceed? Is this clear?
Yes, Professor.
Okay, now the second thing, we also not need to add one. Now if you look at need to add one, so I'm now using another color, and this is actually the color. So this is one. And this, if we convert this one into binary, so this one is, what will be this one? It is actually 0 0 0 0 0 0 0. Any question? This is the binary of one. Any, because this is the binary of one. Okay, now we want to have 4C2. So this is actually C, and we want to have the binary of C2. How many zeros we need to insert in the end? Anyone? 4C2. We want to compute 4C2. Yes. How many zero we need to insert?
2.
2 0. We need to insert 2 0 in the end. So can you see here? So we have 2 0 first 0, because we have 4C, which is actually, now we need to insert 2 0. So now what should I write here? It is actually C0, then C1, then C2, and then C3. And since we also want to add it, so we put another 0 here. Any question? Any question? Should we proceed?
Professor, why did you add three ones for ones complement of A?
Because the thing is, because this A is now a binary number. So now can you see here, this A is now a binary number, and it is unsigned. And since any number which is an unsigned, because when we want to, when we want to add it this, so we need to convert this number into an into its two's complement, because it's a negative A. And how do we,
Oh,
because now
okay, okay.
now the now now the problem is that, problem is that actually A is 4-bit, but if we want to compute the whole answer to avoid loss of data, now we need to add until 7 bits. Got it or not got it? I hope I
Yes, I
answered your
got it.
question.
Yes, yes.
Yeah, this is, and then we will do a lot of more examples, and then you'll see. Okay, now one thing is more left now. Now, can you see here? So now we have something more which is left. So now I'm using now the purple color. So we have C2, and since we have C2, so what should I write here? Help me. Yes, C0, C1, C2, and C3. And since it's an unsigned number, so we need to go. Any question? Any question? This is clear or not clear? Now we
Yes,
want to
Professor.
compute. Yes. Now we want to compute k. Now please remember. So now can you see here? If you want to compute all these things, this will give me what in the end? Help me. The least significant bit will give me what? K0, K1, K2, then K3, then K4, then K5, and K6. And when there will be carry out from here, this if carry out from here, it will give me K7. So now we have proved. Now, if you look at here, all of this K, how many bit of data is this? Any question? Any question? Is it clear or not clear? Can you see here? Now here for K we need an 8-bit. So now we have an 8-bit data. Any question? If there is any question, please let me know, because I will not proceed further until unless there is any question. Yes. This is clear? I'm
Clear,
not hearing,
Professor.
please.
It's
Good.
clear.
So now please remember, I have some headache now, and please remember, if no one is replying me, my headache will, I will have then more headache, but still I'm a little bit have headache today. Okay, so what I'm going to do, so now what I'm going to do, so now please, now I'm going to take this thing off. Okay, and Control C, and then I put it in the next slide. You got it or not got it? So this is how it works. Okay, now we want to use minimum number of resources. We want to use minimum number of resources. Okay, so can you see here the least significant bits? Okay, so now what I'm going to do, so now I'm going to design something, draw what I'm going to do. So now I'm now going to have this thingy. So now what I'm going to do, I'm now going to look into okay, now what I'm going to do, maybe okay, now I'm going to go for this thingy, this least significant stage. Okay, now if you look at this least significant stage, what we need to do? Any question? Someone wants to speak? Yes. Okay, so now what we are going to do, so now we are going to do, so we need a full adder here. So now what we do need to do, so now we need a full adder here. So we need a full adder. Please turn off your mic, because it's just creating some problem. Okay, so we need a full adder here. What is my full adder? So now we need a full adder here. For full adder, we have one input, which is actually A, So now for the full adder, so now can you see here for the full adder, we have A, B, and then we have C in, and then we have C out, and then we have sum. Okay, now please look at here. Now in the least significant stage, what we need to do, we need to add A0 bar 1 and C0. Okay, what will be the value of A here now? So the value of A will be now A0 bar. Now what will be the value of B? So the value of B, I can make it like C0. So can you see the purple color? Okay, so now can you see here in the blue color, it is actually A0 bar. Then the purple color, which is actually what? The purple color, which is actually C0. And then the one, which is actually here, one is here, one is here. What will be my output here? What will be my output here? What should I connect to here? So now actually, can you see here this K, which is actually this sum? So sum will be now here K0. Okay, now please remember, now we have C out, and C out from this stage will become the carry in for the next stage. So now can you see here, this is now the carry out from this stage will become the carry in for the next stage. So this carry out will become the carry in for the next stage. Any question? Any question?
Professor, this is a full adder or a half adder?
This is a full adder. Why this is a full adder? Please remember, if we have zero here, so then we can use a half adder. But since a full adder has three inputs, so for the first input we need A0 bar, for the second input we need C0, and for the third input we need one. If the third input would have been zero, then we would have used a half adder. I hope I answer your question.
Yes, yes. Thank
Clear
you.
or not?
Yes.
Clear? Okay, now this can you see here, so now this thing will go to the next stage, okay. Now if you look at the next stage, now this is my next stage. Now again we have again a full adder, so we have C in here, and then we have C out here, and then we have A, and then we have B, and then we have S. Any question? Any question? No question? Okay, what should I connect to A now? Can anyone tell me? Because everything is in the figure. What should I connect to A? Help me. Yes. No one is answering me. What should I connect to A for the next stage? What should I connect to B? What should I connect to S? Yes, it means
A1 bar.
everyone is. So to A, I will connect A1 bar. Very good. No, it's very good. So now we can say this is A1 bar. And for B, I can connect C1. I can connect C1. And what should I connect to S? Help me for S. Yes, help me.
K1.
K1. Okay, the carry out from this stage will go to the carry in for the next stage. Anyone, any question? So if you go here for the carry in for the next stage, and if you go for the carry in for the next stage, so carry out will be go for the so this is C in, this is C out, and this is we have A, and then B, and then we have S. Then what should for the next stage? What should I connect to the A? Help me. A2 bar. What should I connect to B? Help me.
C2 and then K2. Right.
No. A2 A bar and then C2. So C0. Now first we need to go for C0. Go for C0. Got it or not got it? Okay, now where C2 will go? Okay, please look at here. Now we are going to do, so now we are going. So this is a little tricky. Please remember this is tricky. So I need your attention here. So now what I'm going to do, now I'm going to do for this stage. So now I'm going for this stage. Okay, and now this is this stage. Okay, for this stage we have now A2 bar. So this is A2. This is A2 bar here. And now we have C0. What about C2? Where C2 will go? Can anyone help me?
Will it go as an input to another full adder? The S
Yes.
goes to another full adder and C2 goes to input of
Okay,
that
so now
one.
what we do, so now this is a little tricky. So now what I'm going to do, so I'm now using this color. Why I'm using this color? So now this is we have two outputs, which is actually sum and C out. Okay, So now we have to another adder. So it will go to another adder. Okay. Now this adder. Okay. Should we have C in now at this point of time? Should we have C in now? Help me. No, there is no C in because there are two inputs now. So there should be no C in now. Since there is no C in, so we can use only half adder. Okay, all of these adders are full adders. So this is a half adder. So in the half adder we have A and B, and C is not there, and then we have C out, and then we have sum. And this S will be connected where? Can you help me? S will be connected to what?
K2.
K2. Okay, now what about this C out? Yes.
This goes
But
to the next
we
stage.
didn't use C2.
Hmm?
We didn't use C2 yet.
Which one?
The C2 we
We
only
are
had
mid-stage.
A1, A2, or C0.
Yeah, yes, yes. We didn't use. So this is very, so we need a full adder or a half adder here?
Full adder,
Full.
Full
no?
adder. We need a full adder. So but basically the C out will be we come go to the next stage. So then this go to this A, this go to B, and then C2 will go. Yeah, this is very good observation. This is very good. This is very good. I really like it. So basically what we are going to do, so now C2 is now here. Got it or not got it? Any question?
Okay. So the C out goes to C in, right?
Yeah, the C out go, okay, that's yes, the C out, okay, we can also, yeah, it can be C on or it can be C2, so it can, okay, now we can say it. So now what I'm going to do, so now what I'm going to do, so now what, we can redraw it. We can redraw it. So what we are going to do is we are going to redraw it. Why I'm going to redraw it? So let's assume we want to redraw it. Okay. Now because now this is now a tricky. This is a little tricky because I'm putting, because we have a lot of stuff here. So basically this becomes very complicated. This become very complicated because if I want to solve it in the class, so then I can do it very efficiently. But now it's since we have here, so this is I don't have any space. Okay. Okay. So what I'm going to do, so now we have this thing. So basically, now if you look at here, this C out, and then we have this S. So we need another full adder here. So we need another full adder. And this full adder has C in, then we have A, and then we have B. And for this C out, so can you see here, this C out from this adder will go to the carry in for this stage. And the other input that will go to A and B. This C out from here will go to the C in for this stage. And then what will be the second input? Because A0, A2 bar has been done, C0 has been done. We need to do what? Help me. And this we have S now. Now we have also S. Okay, so now we have S. And this S is now connected to the input A. And now we have B. So now we have B, and what should we connect to B? So we should connect to B. Anyone help me? What should we connect to B?
C2.
Anyone? C2.
C2.
Very good. So now we need to connect to C2 here. Okay. Now since we are connecting here, so now we from this adder we have two outputs, which is actually C out. So now we have this C out here, and then we have C out here, and then we have sum here. Okay. This sum will be now connected to what? Help me.
K2.
K2. And then now the carry in of this will go where? Help me.
The next adder.
The
C in
carry
of the
into the
next
next
adder.
scene of the next set. And this goes on, this goes on, and this goes on. And now you know what I'm going to do. So now I'm going to solve it further. So now this goes on and this goes on, and then solve it further. Okay. Now what are you going to do? So now because I do not have enough space, so maybe I will call this as signal. This is T. Maybe this T. Okay. Now what I'm going to do. So now this is line number 1. So what I'm going to do, I'm copying this, Control C, and then I'm pasting it here. Because the problem is that I cannot solve all the things at once. So now we have T here. So please remember, now we have T from the previous stage. We have T from the previous stage, which is actually the adder, which is actually C in. We have C out. Okay, so the t is from the previous stage. Any question? Got it or not got it?
Got it, Professor.
Okay, so now t is from the previous stage. Okay, now we have an a and b and c in, a and b and c in, and then we have sum, and then we have c out. Okay, now the problem is that now the thing is that, so now we have, can you see here, from here we have C out. Okay, so the carry out from this will become the carry in for this signal. So this sum, we also adding it with this, we are getting this, we have C2, and then we have this thing. Okay, now what should we connect to? Now we are going for the next stage. So now we are going for the next stage. Yes, what should I connect to A here? Help me. Now I am going to now the next stage, and the next stage is, now I'm now showing it in red color. So now this is the red color. This is actually from the previous stage. Yes. Now we have A and B. What should I connect to A? Help me.
A naught.
A0. So now what should I connect to? So this should be actually, now I can use all the, because the colors are too much. So now I can connect A0 here. What should I connect to B? Help me.
A A3 prime.
A3 prime. Okay. Now the question arises. Now so we have A3 prime. Okay. Now we have these two things. So this will go to the next stage. Got it or not got it? And now we have the sum. We have the sum. Clear? This is, now we have the sum of this stage. Okay, so we have the carry out and the sum. Now we have another, can you see here? So now we need another. So this is my C in. Okay. Okay, now can you see here? So now we have another adder here. Okay, so now this is a little tricky, okay. So now we can see here, so now this is actually, now one minute, I need to just go through it. So now let's assume what I'm going to do for K2, for K2, 1 2 3 4. So this is actually, now C out will become the C in. No, I need to redraw it again. I need to redraw it a little bit, because there is a little problem here. There is a little bit problem here. Okay. So now what I'm going to do, should I redraw it again? Because this will create some confusion. So I'm not going to redraw it again. Let's say I want to solve for this stage, K2 stage. Okay. Okay. Now please look at, from here. So now we have the sum here. The sum is here now. Okay. So we need another full adder here. Okay. Any question? Clear? So we have the C out, and the sum will go here, and this is actually, now we have then A, and then B, and then we have C in, and then we have the sum, and then we have C out. Got it or not got it? Okay, so now we have, can you see here, this is now A2 bar. Then we have C0 has been covered. Okay, now what we need to do, so now this is actually, so now this is carry in, will go to the next stage. Go to the next stage. Okay, and now in this case we have B is here. What should I connect here? So A2 bar has been covered, C0 has been covered. What is left now? C2 is now. So now this is actually, C2 is here. So we need a half adder, not a full adder here. So this S will go where? This S will go as K2, and then we have C2. So instead of one carry, we have two carries. Please remember, this is tricky. This is two carries. These are two carries now here. So now these two carries will go to the next stage. Any question? Any question? Clear? Okay. Now please look at
Yes.
here for this stage. Yes. Now because this is a little tricky, because this is now this is this stage, and now this is this stage. So for this stage, so now we have two carries, which is actually this carry and this carry. So let's assume this carry is my T1, this carry is T1, and this carry is T2. Why I'm going, because if you look at this stage, so there may be possible it may generate two carries to the next stage. And since we're generating two carries to the next stage, so now we have T1 and T2. Got it? Any question? Any question? This is clear or not clear? Clear? Okay, so for this thing, so now please remember this thingy is a full adder, and this thingy is a half adder. Now we are going to the next stage. So now we are going to the next stage. So we are going to the next stage, and now we want to cover for the red thingy. Oh, please remember for the red thingy. Now what I'm going to do? I'm now using a red color. So now I'm using a red color, and again we need a full adder here. We need a full adder here, and then we have A, B, and C in. So A, B, and C in, and then we have uh, then we have the sum, and then we have C out. Please remember from the previous stage we have T1 and T2. So we have T1 and T2 from the previous stage. So T1 will come here. Okay, you can connect T1 to A or B, doesn't matter, and you can connect T2 here. Please remember this T1 and T2 are now from the previous stage. This T1 and T2 is now from the previous stage. Since this T1 and T2 is now from the previous stage, what should I connect to B? Can anyone tell me? Because now we are in the red thingy. What should we connect to B? Help me. What should I connect to
A0,
B? Anyone? Huh?
A0,
A0. Very good. Now A0 is connected here. Now if you go for this, so we have now the sum output. Okay, and now what I'm going to do? So now what I'm going to do? So this we have now the sum output. So then we need another adder here. Okay, we need another adder here. This is a full adder. So we need a full adder. So we have actually A, okay, A and B, and then C in. Then we have C out, and then we have S. Okay, what we are going to do? So this S will go to A. What will go to B? Anyone help me? Because A0 has been covered. What should we go to B? Anyone?
A3 bar,
Yes, A3 bar will go here. So A3 bar will go here. So A3 bar will go here. And what will go to C in?
C1,
C1 will go here. Now we have S. It goes back to another adder. We don't know the first in. So now you see there are three inputs. So now remember the full adder is a 3-bit adder. Okay. Now this A is S. Okay. This C out will go to the next stage. Any question? Clear? And actually now we have S. Now we have again this, we have A and B, and then we have C in. What will go to B? Can you tell me?
C3,
C3. So this is a full adder, and this thing is what? Half adder or full adder? The last one.
half adder,
Half adder. And then we have S, and this S should be connected to what? Help me.
K, is that 3? K3, yes.
K3. And then we have C out from here. And this C out will go to the next stage. Okay. Since we have T1 and T2 from here, so now we have T1 and T2 from here. So what should we write here? Help me. Maybe we can say T3 and T4. And this T3 and T4 will go to the next stage now. Now what I'm going to do now, so now can see I can control C, copying it, and now I'm pasting it in the next slide.
Professor, what about the C out from the full adder on top?
Which one?
The C out from the full adder on top,
Yeah,
the
very
red one.
good. T5. Yes, you're right. Got it or not got it? So now basically now we have three outputs, T5, T3, and T anything. Any question? Any question? Yes?
No.
Why no?
No questions, Professor, no questions.
No question. And we have T5, T3, and T7. So now we will go to the next stage now. We will go to the next. Okay, please now remember we have now three carries from the previous stage. Very good. It was a very good observation. I really like it. I really like it. Thank you. Thank you very much for this. And now we look good now. So now we have T5, T6, and T7. Okay. Now what we are going to do now? So basically what we are going to do. So now we are interested in another stage, which is actually now, okay, we solve for K3. Now we should solve for what? Help me. Now we want to solve for Q. For K4, now this is my K4 now. And this we have A, B, and then we have C in, then we have sum, and then we have C out. And please remember, we have three carries from the previous stage. So we from the previous stage we have T3, then T4, and then T5. And this is S, and then we have C out. C out will go to the next stage. Maybe this is T6 now. Now we need another adder. Okay, we need another adder. So now can you see here? Now we need to add what? The sum is from here, and then we need to add A1 here. Okay, and then we need to add 1 here. Then we have S. When we S, so we have T7 now here. Since we have an S here, and we have 3-bit adder, so this is S, and this will go to another adder. So A1 is now done, 1 is now done, and then we need C2 here. So this should be a half adder or full adder. So this is a full adder, and this is
Half
now
adder.
half adder. And then what will be the output here? Help me. T8, and this S should be connected to where? Help me. This
K4.
S. K4. Now we go to the next stage. Now this is the thing. Then the interesting thing is this. Now we go to the next stage. So when we go to the next stage, now we are in this stage. So what I'm going to do? So please, I need your attention. I still have headache, but still I want you to be more and more attentive, because if you are more and more attentive, I will be happy. So now what you can see. So now Control C, and then I'm pasting it here. Okay. Now we want to solve for this stage. So we want to solve for this stage. So can you see? I can make another color for this. We solved for what? K4. Now we want to solve for K5. We want to solve for K5. For K5. So for K5 we have what? We have A, B, and C. And basically now we have to. So now we, from the previous stage, we have T6, T7, and T8 to T6, T7, and T8 from the previous stage. Okay, and then it will give me the S, and this will have the C out, and C out, it is actually T9. This is the next stage. So now we have another adder here. For the net adder here, so now we have A2 here, and now 1 is here. So N is here, so now we have an S. Okay, and then we need another half adder here. And what should go to this half adder? This is the S, which is actually the half adder, and then it will be C3 here. Then we have T10, and then this half adder is T11, and then we have S. S should be connected to what? Help me.
K5.
K5. And then if it's connected to K5, this is now connected to K5. Now we go to the next stage. We go to the next stage. Okay. So when we go to the next stage, you go to the next stage. Let's assume we go to the next stage. Now we go to the next stage. What I'm going to do, so I'm going to copy this and paste it here. Control C, and I'm pasting it here. So now let's assume I want to solve this using the red color, and the red color is now this thing. So we solved for what? We solved for K5. Now we want to solve for K6. So for K6, now we have what are from the previous stage? T9, T10, and 11, T9, T10, and 11, T9, T10, and T11, and then we go to the next stage. Okay, so this is actually T12, and we go to the next stage. So now we want to solve for here. So what is the second input? A3.
1.
Yes, and then 1. Got it or not got it? And then we have sum, and now we have sum. Please remember, this is not my sum. Now this is my sum, and this is not C out. C out is actually T13 here, and T13, this sum is what? Can you help me? This is what? Help me.
K6.
A6. Now we have another stage. So now we have another stage. So now if we have another stage, so if we go to the another stage, okay, we can do it now directly here. We have another stage here. Okay, so what I'm going to do, I'm now using it with another color. So basically we have T2 and T13. We have T2 and T3. Any question? Yes or no? So for the last stage, What we need? Can anyone help me?
Half adder.
We need a half adder. Got it or not got it? And this half adder will give me K7. Any question? Clear? So this is how it works. This is how it works. And then, this is the thing. So this is how it works. Any question? Oh, sorry. This is a little small mistake here. This is small mistake here. This is small mistake here. This is small mistake here. So basically, we have case 6 here, and I think so. This T1 may go to the next stage, and then this T13 will be case 7. I will provide a complete solution for this. This is just like I will solve this question again and completely, and then I will have the complete solution. Now you know how to solve at least the question. Anyone? Yes. Yes.
Professor, can you explain why T12 goes back into the adder?
Because the reason is that we make we make a small mistake in the previous stages, because if since we computed it, so basically the output should be now or 8-bit data, not 9-bit data. Because can you see here, if we cover this thing T3 and T, so it will give us 9-bit data, not 8-bit data. I hope I answer your question.
Yes, Professor. Thank you.
Because so maybe there is some mistake here, because we did a little bit mistake in all the steps, and I cannot go through, but I will go through there, and I will provide a complete solution to you. Because we calculated first. So basically, when we calculated this thingy, so when we calculated this thingy, so 8a plus 8a, so basically now the data should have been how many bits for us?
8 bits.
8 bits.
The data should be in 8 bits. So the data should be in 8 bits, and the data should be in 8 bits. So there is a some problem. So basically, we can solve it this, and then I can provide an explanation for this, that how it will work. Any question? Yes. Got it or not got it? So now we have, okay. Now can you see here? So now we have how many carries from here? So T5, T4, T3, T3, T4, and T5. Again, these are all the stages from the previous stages. We are adding it with A1. So maybe there is something. So T1, T3. Which stage is this? So maybe there is a small mistake here. Got it? But I will provide a complete solution on island. But you need to know that how the working is going on. Got it? Okay, so now this is your homework. So let's assume if you want to compute t is equal to 5a plus 9b, you can also solve it. Okay, now what is a gate delay? What is a gate delay? Can you tell me what is a gate delay? Can you answer me what is a gate delay? Okay,
Is it
now yes,
is it like
Mubin.
when a process doesn't happen instantly? So maybe like the
Yes,
zero.
if I ask any question from anyone, let's say I say, okay, what is your name? You say, okay, my name is Mubin. Basically, when I ask you a question, you didn't reply me instantaneously. You reply me after, you reply me after some delay. This is called as the delay. This is the human delay. Okay. Similarly, every gate has some delay. Now, if you go for this, so this gate has a delay of this. So can you see here? So now I'm going to do. So now can you see here? Now I'm going to do copy, and then I'm making it pasting here. So now can you see here in this example? So now my input. So this is a gate. Which gate is this? This is an AND gate. If this is an AND gate and the output is Z and the input is X and Y, and it has a gate delay of tau. Why it has a gate delay of tau? So now we say this. So ideally, when X is equal to 0 and Y is equal, what will be the output? 0 and 1. The output should be 0. What is my output? My output is now I'm now drawing it in red color. So now this is my Z output. So this is actually the ideal input. So the input is 0. So now at this point of time, so can you see here? This is T1. At T1, X is make a transition from a 0 to 1, and Y is the same. So basically now the input is 1 and 1. What should be my output? So my output is 1 here. So this is actually the ideal gate. The ideal gate has zero delay. So now can you see this input X make a transition from 0 to 1 instantaneously, and this Y is actually same, so this make X is, and this, remember this, the instant, this transition is not real. Actually the transition is something like this. So the transition is something like this. So we call this as the rise time. This is called as the rise time. Now if you look at here, now actually this is the ideal gate which has a zero delay. And if you look at here, there is actually, can you see here in the in this color, so this is actually the real delay, the real gate. And what is the delay of this? So the delay of this is tau. Clear? Any question? Should we proceed? Should we proceed? Okay, so now what is the gate? So a gate, a change in the input of a gate causes the to change its output. However, the change in the output is not instantaneously. So can you see here? So now the input has here, the
Professor,
input
we
has
can't
changed.
see your screen.
You cannot see my screen now.
I know we can't see your screen anymore.
Now you see my screen now.
No,
No.
not yet.
Why? I don't know. Oh man, maybe this is, I don't know. This is happening on now. Can you see my screen now?
No, Professor, no. Okay, now, yeah.
Yes.
Okay. Okay, so now this is the instantaneous delay. Okay, got it or not got it? Okay, so can you see here now? Now, if you look at here, so now consider the circuit for the eight inputs. So can you see here now? How many gates are here? How many gates are here?
6.
There are 6 gates. Okay, what is the delay for two input AND gate? So the delay for two input AND gate is 2 nanosecond. The delay for three input AND gate is 3 nanosecond, and blah blah blah. Okay, now what I'm going to do? So now I explain this. Copy, and then okay. Now what is the delay of this AND gate? Can you tell me? Because of two input AND gate has a delay of 2 nanosecond. So this gate has a delay of 2. What will be the delay of this gate? Can you tell me? Yes,
3.
3. This is 3. This is now 2. This is now 3, and this is now. Now we consider different paths. We consider different paths. So for this circuit, so we have two outputs. So this circuit has one, two. There are some inputs and there are two outputs for this circuit. So these are two outputs for this circuit, and these two outputs are F and G. Now we need to consider different paths. So now this is my path 1. Can you see it? This is my path 1. What about, is there any other path? P1. Yes, then there is another path. I'm not doing it in draw. So this is another path. So can you see here? P2. There is another path. Can you tell me this path? Yes. P3, and then there's another path which is actually P4. What is the delay of path 1? Can you now tell me what is the delay of path 1? Yes, help me.
4 nanoseconds.
2 and 2 is actually 4 nanosecond. What is the delay for path 2? Yes.
5.
What is the delay for path 3?
8.
And what is the delay for path 4?
8 again.
8 again. So okay, what is the critical path delay? So the critical path delay is actually the maximum delay from all paths. So here for this particular example, what will be the delay here in this example? What is the critical path delay here for this question? Yes, anyone? Yes.
8.
Wait a second. Any question?
Professor, I have a doubt.
Yeah.
Shouldn't there be a fifth path from the first two input
Yeah, there can be
and
multiple paths. Yeah, there can be multiple paths. But if you go to the critical path, so there can be, yes, multiple. You can also be on multiple paths now.
okay. Thank you,
Right.
Professor.
Okay. You say you called for path 5. Yeah. So this path 5, I know that this path 5 is like here, from here till here. Yeah. Yes.
Yes, Professor.
Yeah, I got it. I got it. So now you can also have path 5, P5, and you can calculate the delay for path 5. So whatever what you do, so we want to compute the critical delay, we consider all of the possible paths, and then we see what is the maximum delay. Any question? Any question? Okay, now can you see here now? Now this is hmm. So now can you see here now? Okay, can you see here? What is this thingy? Can you tell me this is what is this thingy? Can you tell me what is this thingy? Anyone? What is this thing? Help me. So what is this thing? Can you what has been shown here? Anyone may answer. What is this thingy? Yes.
Is it just a 4-bit adder?
So this is actually the gate level. So now what we do? This is not this is so because this is the gate level implementation of a 4-bit adder. Am I right? Okay. Now can you see here conceptually, this 4-bit adder consists of how many full adders? So this red thingy. What is this red thingy? Help me.
Full adder. 4 full
Full adder.
adders.
And this also, can you see here, this is also the full adder. So that's because we are designing it as a full adder. So this is a full adder here. Got it or not got it? Okay, now this is a full adder. Okay, and if you look at it, this full adder, so this is actually what? A, B, and this is my C in, this is my sum, and this is my C out. Am I right? So this is my A, and this is my B, this is my C in now. This is my sum, and this is my C out. Any question? Any question? Should we proceed? Okay, now if you look at this full adder, so can you see here now? Let's assume this is my one full adder. So this one full adder, this is a full adder here. This full adder consists of two half adders and consists of two half adder and one OR gate. So can you see here? Please remember, what is a half adder here? So now in this case, now this full adder consists of two half adders. So what is this thing? Help me. What is this thing? A half adder. And what is this thingy? Yes, is also a half adder. And then can you see here? This is now my what is my this thingy? So this is actually OR gate, and we already studied it. Any question? Any question? Clear or not clear?
Clear.
Okay, now what we are going to do now? Now this is another thing. This is from the now this is the gate level. So can you see here? So now this is the gate level implementation. This is now the gate level implementation. This is now the gate level implementation of the and suppose the delay of the exclusive OR gate. So what is the delay of the exclusive OR gate? So this delay of the exclusive OR gate is delta 1. So the delay of this exclusive OR gate. So can you see here? So now this the delay of this exclusive OR gate is delta 1. Okay, and this is delta 1 is shown in green color, and the delay of the AND OR gate. So now the delay of this AND OR gate, so this is the delay of the AND OR gate, so this is now the AND OR gate. Got it? So this is delta 2. Control, make it control C, so I can use a different color, maybe the blue color, so now I can see the more color standard, so I can see the blue color. Okay, so this is delta 2. So this is delta 2, this is delta 2, this is delta 2, this is delta 2, and this is delta 2. Got it? Okay, now if you want to compute, so now since we have this thingy, okay, so now what we can see, if we have this thingy, so now there are two critical paths here. Please remember, there are two critical paths, and now I will show you this critical path. There are two paths here. Now this is the path, this is the critical path, this is the first path, this is P1. So this is the critical path for C4. And if you look at the critical path for C4, so the delay of C4 will be what? Delay of C4 is now what? Help me. Can you all tell me? Delta 1 plus what? Delta 2 plus delta 2 plus delta 2 plus delta 2. And what is the delay? So delay will be actually delta 1 plus 4 delta 2. Any question? Any question? Okay. Now, if you go for this, control C, and then I can say paste special here. This is one path. So now can you see here? This is another critical path here. So now there is another critical path. So now the other critical path that is in here, that is shown in the green color. So that critical will go from here to here, here, and here. What is the delay of S3? Can anyone tell me? Yes. Delta 1 plus delta 2 plus delta 2 plus delta 2. So what is now the delay of S3? Can anyone tell me? Help me. Delta 1 plus, help me. Please speak.
3 delta 2.
Yes. Okay. Now in general, so can you see here what is the general formula for? Can you see here? So now what I'm going to do? So I'm taking a screenshot of this.
Professor, isn't there a
Yeah.
second delta 1 for S3?
Which one?
For S3, there should be a second delta 1, no?
Yeah, you're right. You're right. Yes, you're right. So this is actually plus the last delta 1. Yeah. Since the last delta 1, it is actually 2 delta 1 plus 3 delta 2. Got it? Because this is the last one. Got it or not got it? So now can you see here? So now what I'm going to do? So now what I'm going to do? So now we can also do this. So basically, what is the delay for this S3? So please remember. Now we have control V. So what is the most significant? Okay. Now please remember. Now can you see here? So what I can do that? So I can take a copy of this. Control C. Copy. Control X. And then I'm pasting it as an image. Okay, then what I'm going to do, I'm going to copy this and I'm pasting it here. So what is the delay of N S3? So the delay, because this was a 4-bit adder. So can you see here, this was a 4-bit adder. Since this was a 4-bit adder, so N was 4 now. Since N was 4, so we want to delay Sn minus 1. So what is Sn minus 1? So Sn minus 1 is actually 2 delta 1 plus N minus 1 delta 2. So what is S? Now it is 4. It is 4 minus 1 is actually 2 delta 1 plus N. What is N? 4 minus 1 delta 2. So now S3 is equal to 2 delta 1 plus 3 delta 2. Got it or not got it? So now this is the general formula. So now can see control C, and you know what I'm going to do. So now I'm going to, is there any, I need to insert a new slide. Copy, and then I'm pasting this question. Okay, so now can you see here? So now this is the general formula. So this is my general formula. So now I'm pasting it here. So what will be the delay? So what is the delay of a 32-bit adder? So the delay of 32-bit adder is actually Sn minus 1. The delay of Sn minus 1 will be actually 2 delta 1 plus N minus 1 delta 2. So S32 minus 1 is equal to 2 delta 1, and it is actually 32 minus 1 delta 2. So the delay of S31 will be 2 delta 1 plus 31 delta 2. Any question? Any question? Okay. Now similarly, using the same argument, so now we have this the delay of C4. Can you see here? This is my delay of C4. So now what I'm going to do? So now I'm going to do here Control X, and now here we are here. Okay. So now what I'm going to do? So now we already calculated the delay of. Can you see here? This is Control C, and then I'm pasting it here. So now I'm pasting as an image. This is my delay of C4. But you know what is the general formula for delay of C4? And the general formula is there, it's already given here. So the delay for this, so I got good, I think print screen for this. Okay, and then I'm pasting it here. So what is the final C out delay? So now for an 8-bit 4-bit adder, so for a 4-bit adder n is 4, so C4 will be actually delta 1 plus n delta 2, n is 4, so it is actually n delta 1 plus 4 delta 2. So what will be the delay? So using the same argument, so if we say what is now the delay of 32-bit adder, the delay of 32-bit adder, what can you tell me? So the delay of 32-bit adder will be what? So this is actually C32 will be actually delta 1 plus 32 delta 2. Yes, any question? Any question? Should we proceed? Yes, any question?
Yes, Professor.
All
Professor,
clear? Yeah.
is C32 greater than S32 most of the time? Like is the delay of the carry more than the delay of
Because
the
the thing is, basically the thing is, if you're adding to n-bit number, if you're adding any two n-bit numbers, so the result will be n plus 1 bits, because there is an additional 1 bit which is actually in C out now. So we need to also cater them into account if we want to use it in future. Got it or
Okay,
not
but
got
I'm
it?
saying in general, would the delay of the MSB be higher than the delay of the carry? Or sorry, the other way around.
No, so the thing is, basically the thing is, let's say if we want to compute the result as a 16-bit data. So we have a 16-bit and we have 32-bit adder, for instance. Okay, so we will not be interested in C32. We'll only considering the delay of like the least significant stages, not the most significant stages. But when we are considering
Okay.
the delay of an n-bit adder, so we need to consider how much time it requires to ripple the carry from the least stage to the most significant stage. I hope I answered your question now.
Yes, I got it. Thank you, Professor.
Okay, so this is how it's done. Okay, so what I'm going to do now, I'm now stop recording.